Chess is a game that has been played for millennia. It's fascinating to study, and it has caused many people to be able to build an entire life and career from it. In the 90s, chess was slowly taken over by AI, such as Deep Blue, which ended up being able to solve chess through algorithmic computation. In this video, we're going to look at an AI that uses reinforcement learning, which learns like a human, to learn how to play chess and see how my journey in building that and understanding how it works went. So, let's start with it. First, let's visualize what chess would look like to an AI that can only read numbers and not see the board. Chess is a game played on an 8x8 array with different types of pieces that can all be represented as numbers. Each number moves in different ways, such as moving up one square or left one square, or down one square or right one square, and so on. And some pieces can be blocked and some pieces can't be blocked. And there are rules such as castling and en passant and double moving and flagging and 50 move rule and 75 move rule and capturing and checkmate and stalemate. And all of these rules end up amounting to a very difficult game for the AI. It's a lot to take in for a person, so how can an AI manage it if they can't see the board? AI use an algorithm called minimax. Now, how minimax works is that first you need to evaluate the position. Evaluating the position can work in different ways, but here, in this case, we're using the amount of material or how many pieces you have and what value they are. Now, each move branches out from the original starting structure. So, for example, if you look at one of the branches, we just moved a pawn and they captured a bishop, which ends up meaning that the opposing team is up a queen, but we aren't. So that's a 9-point loss for us. On the other hand, if he captures their queen, that's a 3-point gain for us instead, which means that that's better for us. The opponent is always trying to minimize our gain, and we are trying to maximize it. Hence the name, Minimax. Now, let's look at how reinforcement learning can be used to make chess AI like this. Now, the way reinforcement learning can be used is in a format called Q-learning. Let's imagine a case. There are 3 different chats that we can access, those being a party, a chat with a friend, and an interview. And there are 3 responses. Cool, bro. That's amazing. And I think what you're doing is fascinating. Saying that last one at the party makes you look like a dork and makes you lose the conversation. So we'll mark it as -1, so very bad. On the other hand, at the interview, that makes you seem much more interested in the conversation, which is good for you. On the other hand, saying cool at the party makes you look like the cool person, because you are, but saying it at the interview makes you seem like you're not interested in the conversation. And so on and so forth. Now, in the end, we replace the responses with moves and the chats with positions. And this is how our AI will end up working. So, let's look at it in live action at Google Colab, which is what I use for this project. Now, we'll be working in Google Colab because that's the environment I use for this AI work. First, let's install the chess library. Now, after installing this, we're going to have some support. For now, we won't be using this, but it is what we'll use in the future if we choose to develop this any further. Now, after that, we first do our imports. Now, this is the code for the move chess object. In this case, we'll be splitting our objective of Q-learning for chess into a few pieces. To start off with, let's play move chess. In move chess, we have a piece and a target, and we can move in any direction in any distance. So for example, I can say 5, 1, and the piece will move 5 down and 1 to the right. Now it's just 0, 4, at which point we've reached our target and we win. Now, our next demonstration is the move chess algorithm itself. This one uses the Q-learning algorithm in order to create a board. Now, this was a self-coded version that ended up not being able to work. We'll discuss about what happened here later, but first let's focus on the actual end result. Now, taking inspiration from Aryan Khun's final board, this is the end result. The way this works is that there is a two-dimensional matrix of sorts, which represents a chessboard, and there's a piece represented by S for start and the target represented by F for finish. Now, we make an array of numbers that represents the evaluation of each position. So, if the piece was in that position, how good it would it be? And because we are trying to minimize the amount of moves taken, we try to um, minimize the evaluation when it gets further out and maximize it when it gets closer in, as that means we can get there faster. Now, after setting up this grid, we can run an algorithm that converges the evaluation. This is our policy evaluation function. Now, once we've done this, we end up getting a bunch of values. And after normalizing using a bunch of iterations, we eventually get the optimal policy. Now, this is for the king, meaning that it's distance based. So the closer you are, the higher the evaluation is. And the evaluations are negative because we want the AI to be punished for taking too long. Now, the following is the code for Q-learning. Unfortunately, this didn't end up working because, as you can see, if I run this, we end up having an error with a tensor. To be specific, that's the NHWC tensor. And instead of that, the data ends up giving the NCHW tensor, which it does not work in this case due to GPU support limitations. I haven't been able to figure out how to fix this with Keras, and I couldn't find any guides, which is why currently the code has stalled here. But the way this code works is that after initializing the board and the AI, which is called the agent here, we start Q-learning. Q-learning works as we talked about in the presentation, with there being a big table of different values for different moves and different positions. And in the end, once this is done, we end up fixing the model, meaning that we put everything together to make it work, and then we make the AI learn. Now, after this, the AI would be able to play a game. This AI doesn't just work for move chess; it also works for capture chess, which would be the next stage in our process. To be specific, in capture chess, you have a chessboard with pieces set up normally, but the goal is to capture as much material as possible, like in the Minimax example that I showed before. Now, as for the non-functional code, I ended up spending a lot of time programming on this one specific project, and it ended up taking a lot of energy from me. In the end, even though it didn't end up working, I still feel like I learned a lot about AI and reinforcement learning through this. And Aryan Khun's Kaggle repository was a godsend for me at this point. Without it, I wouldn't really have been able to get as far as I did now. Now, let's talk a bit about what happened in the end of the project. Now, as you have seen from the code and the presentation, the project did not go exactly as planned. In the end, it ended up failing during the capture chess stage, which meant that I wasn't able to progress any further. But during this, I learned a lot about how to deal with failure and what a replicate truly means. And while I can't go fully through it in this video, I did write a lot about it in my article, which you should go check out, by the way. And I feel like it was a really good learning experience for me in the long run. And I'm going to use a lot of what I've learned here in the future for my second replicate, which is coming soon. Other than that, thank you for watching, and I'll see you in the next video. Bye.